everyone, and welcome to TigerBeetle Show, a show where we look at this exciting, awesome new database for financial accounting called TigerBeetle and try to understand how that thing actually works inside. In a sense, we go through the entire database, read every single file, and learn how to build this thing ourselves. What is cool about TigerBeetle is that this database doesn't use, among many things, doesn't use any dependencies. And this in turn means that if you understand just all the code in the TigerBeetle's repository, you essentially understand everything there is to build modern databases. Okay, so what have we been up to lately? We've looked at how time works. Specifically, last time we looked at the theory behind time. We discussed the three classes of time: monotonic stopwatch time, then real world, like UTC quote quote real time, and then the horrible human mess, which are time zones. So today we are going to, oh yes, and what also we've discussed last time is that we briefly looked at the operating system APIs to get specific time. So you essentially call get clock or something like that. And that gives you either stopwatch time or real time. So today we are going to look at the actual code, which takes time samples from multiple replicas, and looking at all of them comes up with the so-called cluster time. The time which is more reliable than a time of any single one particular replica. Okay, and yeah, this code is actually very much inspired by and resembles and actually even borrows some terminology from network time protocol. Because essentially, yes, essentially we are like network time protocol, the protocol used to transfer time is actually hierarchical. So time is maintained by super precise satellites somewhere in space, but when you need to sync time on your mobile phone, you are not actually going to talk to the satellite. You are going to talk to a server which maintains time, which is close to you. And even that server, it won't directly talk to the satellites. It actually would talk to some server which is a little bit remote, but still pretty close to you. So there is like this natural hierarchy. And what we are going to do today is that we're going to extend this NTP hierarchy one level down to make sure that replicas also exchange clocks around each other. Okay, I guess let's get our code sharing up and let's drive straight in. Okay. We are going to look mostly at the clock.zig file today, and again, it starts with very large command which explains how it works here. But if you don't want to read the comments, then please watch this video stream. And to start with the middle, there's this synchronize method which contains the loop which we've talked about last time. So again, we have here clock measurements from a bunch of replicas. And we need to figure out what is the actual real time given all the clock measurements we have. The way we do this is that we start with like error margin with the tolerance, which is config clock offset tolerance, which is 10 seconds. Okay, so we start with error margin of 10 seconds and say, okay, so if each clock on a replica gives a correct answer within 10 seconds, so you know if the clock says it's like 32 seconds past 9, it might be anywhere between like 32 seconds to 52 seconds past 9. Okay, so we say, okay, if if each clock has an error margin of like 10 seconds, is there some interval which is intersected by clocks of at least half of a cluster? And if there is in fact such an interval, then we go and try to reduce error tolerance. And so we kind of like find the smallest tolerance, which still allows us to have this interval, which is intersected by the clocks of at least half of the nodes. And the smallest such interval, which is going to be just a single point, is going to be our real time real. Okay, so that is the middle of things. Now let's start properly from the beginning. The time goes through ping and pong messages. So in the ping message, somewhere we include time. Yeah, we include ping timestamp monotonic, and this is a ping. And then we have pong. And in pong, we include ping timestamp monotonic and pong timestamp wow. So what is this? Why do we need like one time in ping, two times in pong? So what we want to do is that for every replica in the cluster, we want to learn about this replica's time. But other replicas cannot just tell us their time. The only way they can communicate the time to us is by sending a message, which has to travel over the network, which has a delay. So if a replica looks at the clock and says, okay, it's 9:30, and then it packs this 9:30 into a message and sends a message to us, by the time the message gets to us, it is no longer 9:30 according to that replica clock. So we need to somehow estimate network delay. And the way we do this is that if I want to learn your time, I go and send you a ping message. And I include my clock, my monotonic clock in this ping message. You, when you receive this ping message, you're going to respond to me with a pong, and you're going to include your time in this pong. But you also are going to transfer this ping timestamp from ping, which results in a pong, to the pong. So when I receive a pong, I actually have two timestamps. I have your timestamp, but I also have my timestamp from the time when I was sent a ping. So now, if I look at my monotonic clock again and look at the difference between this most recent reading and the reading which is there in the pong, I would actually can estimate round trip delay. And we'll get to it because it's going to be pretty fancy, but just dividing this by 2 will get me an estimation of 1 way delay, which would allow me to understand what is the actual wall clock time. Okay, so let's see how this happens. So on ping timeout, a replica goes. Is the font a little bit on a smaller size? Let's make it 26. On ping timeout, replica broadcasts ping message to actually everyone, and it includes monotonic timestamp into the clock, and the monotonic timestamp, as we've learned yesterday, a week ago, is more or less just directly asking the operating system for monotonic timestamp, plus also actually ensuring that it is monotonic because the operating system, or rather the underlying virtual machines, sometimes lie. Okay, so that is the ping. Then we receive the ping on ping, and we send the pawn, and then we include Ping's timestamp in the pawn and our real time, where real time is again just a reading from operating systems clock, but this time we kind of like don't try to make real time monotonic, because real time is not monotonic. Real time cannot be monotonic because the clock drift, and periodically your clock actually needs to get adjusted. Okay, so then when we receive the pawn back, we actually extract 3 times. The original time of the ping, then our current monotonic time, and the real time of the other replica from the time when it received ping message. And then we go and tick and like ask the clock to learn stuff. Okay, now let's dive into the implementation of a clock, and rather than following from learn, let's maybe try to read it top bottom, because and again, this is a warning which I periodically give, is that I haven't, before the stream, I haven't thoroughly studied the code of a clock. So I understand in like broad strokes what it does, but I don't know details. And details is what we're going to look at today, so we'll be figuring this out together. Okay. So we have samples, and we have epochs, and then we have epoch two. We actually have 2 epochs. We have epoch and we have window, and then we have Marzullo tuples, and we have synchronization disabled, and quorum and replica and time. Okay, it doesn't make a whole lot of sense to me. So let's try to let's try to figure this out together. Okay. Well, replica and quorum is relatively easy. So replica is usual a replica index which is used for login, and I think it would be useful to distinguish our clock reading from other clocks reading. Quorum is how many clocks do we require to consider the clock to be synchronized. And if I remember correctly, we set quorum to be replication quorum, so half of the replicas in a cluster of 6. Okay, so replica quorum is easy. Time. Time is the underlying operating system source of time information. And then epoch. So I guess when I guess the way this works is that we kind of like accumulate samples from other replicas, and we probably accumulate this in a window, and then once we realize that a window contains enough samples, we kind of like convert that window to an epoch and say, okay, epoch is like some time ago we had time synchronized, and at that point the time was synchronized to do this. And Marzullo tuples is something related to that algorithm for finding the smallest interval which intersects at least half of the clocks. And inside, well, okay, let's now get back to the sample and debug. Again, it's not, doesn't make a lot of sense to me, but well, we'll see. So sample. Sample is the time we learned from a replica, so replica's real time, and the delay. I'm not entirely sure how this is set up, so let's kind of like skip about this. Okay, in the epoch, we have an array of optional samples. So for every replica from which we learn the clock, we are going to put it in a sample. But if we haven't heard from replica, we put null there. Then we have the samples, which probably is the number of non-null elements of the sources array. Okay, then the 2 times when the epoch began. Again, 2 times because there's real time and then there is monotonic time. And I guess like now this clock offset makes sense to me. So this is our real time, and probably to get real time on another replica at the point of an epoch start, we are going to add clock offset to this real time. Okay, and what the hell is Marzullo interval? Okay, this is that smallest interval which is consistent with like a required number of replicas. Okay, so yeah, reset is pretty clear. So we always have one sample, and this sample doesn't have a delay. Okay. Samples. Oh, okay, let's see from there. Okay, initializing the clock. We know the total number of replicas, so we allocate our sources for one epoch, and we allocate sources for another epoch. Okay, now I don't understand how do they do this. Okay, we have Marzullo tuples in the clock. Do we have one in the epoch? No, we don't have one in an epoch. Okay, probably it is just a scratch space for our algorithm, but well, we'll see. And we reset both epochs. As a sanity check, we see 3 statements in the init method, so there should be 3 error differs in the init, and it appears to be so. Okay, so that makes sense. Okay, now let's see how we learn. Again, we learn clock sample from this replica. This was our stopwatch when we send the ping. This is the stopwatch when we receive the pong. And this is the real time of another replica when it received ping. Okay. If M0 is larger than M2, so kind of like we observed that our monotonic time went backwards, this actually shouldn't be possible because, well, our time is supposed to be monotonic. I guess what could happen is that we know that certain virtual machine operating system combinations have bugs, and we protect against those bugs in our source code. But that protection obviously lasts only while our process lives. So what could happen is that you send a ping, and then you crash, and then you restart, and at the same time, like operating system bugs you, and the time goes backwards, and that is the case where you'll get here, but that feels like super rare. So actually this might even get upgraded to the error, because it is kind of like this should be like either a bug or something like really messed up with time. Okay. I guess this is another thing. We need to make sure that this ping is actually recent. So if this ping is before our current window started, we kind of like also reject it. And well, uh, this one actually also should be error, I think. And this one should perhaps even be an unreachable, because even if a process crashes, you shouldn't be able to get your M2, so the current reading, less than the window monotonic. But well, again, let's kind of like keep it this way. Although like this one should be a warning, because I think this one could genuinely happen if messages are just delayed by the network. Okay, so then we calculate the elapsed. It is the time from the start of our window. And if this is larger than our like window when we collect samples, then we like also ignore this. And what is okay, I am lost. Okay, I am completely lost. I wanted to check what is window max. So window max is clock synchronization window maximus minuses, and this in config window min max. So we try to collect samples for at most 20 seconds at any given point in time. Okay. So if this window is like too obsolete, then we also ignore a sample. Okay, then we have like round trip time, and then we have simple one-way delay. Wait, what? Okay, so I think the two here is like our real time at this point. So window real time is the real time when we started the epoch, and T2 is essentially self clock, self time, real time, because it's just like the elapsed plus the start. But I guess we don't want to call real time a second time, because again, real time could be adjusted. It could go forwards or backwards, and here we just don't want to think about this. We said, okay, we did our real-time measurement once at the start of a window, and we're going to stick to this. Okay, so yeah, so T2 is what is like our current real time. Then T1 is the real time of the other replica when it received the pong. So T1 plus one-way delay is the real time that the other replica thinks it is right now. So okay, T2 is what's our real time currently, and T1 plus this thing is what other replica thinks is the real time now. So clock offset is that thing minus T2. In other words, if we add clock offset to our current time, then we'll get the time that the other replica thinks is currently is. Okay, and that is the clock offset. We get like using naive estimation by just dividing a round trip time divided by 2. So apparently then we try to estimate asymmetric delay because, I mean, there is no guarantee that the round trip time is exactly the same. It might be the case that, like, the packets take more time to travel in that direction than to go back because, well, they might actually be following different roads or whatever. So, well, we'll look at this in a moment, but basically then we compute this actual offset. And this gives us a sample. So we have this clock offset, which is using corrected one-way delay. And then we do like half round trip time here. So it's just, I mean, this is not one-way delay. It is round trip time divided by 2 because like one-way delay we are estimated here. I'm wondering if it's just confusing name or if it's actually some bug in our clock implementation. This is exciting. Okay, let's see. Okay, then we say that we've learned one more sample. Oh, actually, no. I don't think this is the number. I said that the sample is the number of like non-null things, but no. Actually, it seems like that is just like the total number of samples we've collected during this window, which means that if we collect samples for the same replica, apparently we pick the sample with smallest delay. Well, yeah, kind of like we kind of like if we have several ping-pongs from the same replica, then we pick the one which had lower round trip time. And okay, at least for this point, using one-way delay is correct. Let's see if it is used. Okay, what is epoch? Okay, so this is definitely bad variable naming because I mean this is not an epoch. This is a source because sources contain some. Well, it's okay. This is sample. This is not epoch. This is sample. Really? Okay, I'm just going to rename as a sample because it's definitely not an epoch. Okay, sorry. Where was it? Okay, one-way delay. Okay, we apparently use this a bunch. Okay. Okay, but like okay, minimum one-way delays is relatively clear. Well, let's die this estimated asymmetric delay. This is so estimated asymmetric delay is very explicitly a function which I've read the name of and haven't looked at the implementation at all. So I will try to fry my brains a bit to understand how it works. Okay, so we have our clock, we have our replica index, we have one-way delay. Which is like I'm yeah which is like, I still object to naming this one-way delay because it is round trip time divided by 2. Okay, we have like half of RTT, and we have clock offset. Okay, so if we already have a sample for this replica and our current round trip time is less than the round trip time from that existing sample, we actually say that, hey, asymmetric delay is 0. Well, okay. Okay, no, I don't understand this. If clock offset is larger than clock offset, but why would they be different? Okay. Okay, I don't understand this. So okay, let's try to work it out. So we compare the sample clock offset, and we compute like clock offset as just like time plus half of a symmetric delay. Okay, this really doesn't seem correct to me. It seems like this actually would be the same. Okay, yeah, yeah. Okay, so yeah, I guess kind of like we could somehow like, okay, the idea is clear to me. We have a bunch of samples, so we want to execute to estimate asymmetric delay using like this fact that we like have multiple measurements, so we can correlate them against each other, and probably reading this paper would actually be a good thing to understand how this works. But this one like doesn't make sense to me because it seems like this computation is actually stable. Okay, so let's do something like this. Okay, so let's say that we send ping a time bear, and okay, let's make it like super extreme. We've sent ping in time r. It arrived at a time r plus 10. And then we received the result in a plus 10 again. So actually, like, you know, the delay is fully Edwin Cheng. Hello, Edwin. I've worked with Edwin back at Rust Launcher. Well, like work. Like Edwin actually, like, you know, wrote the entire macro expansion machinery and whatnot. So he's like super. It's nice to meet all internet friends. Okay. Sorry, Edwin, you derailed me. Okay, we have asymmetric delay. We have delay of 10 something, and it is fully concentrated on one path. So this thing is going to be 10, and this thing is going to be 5. So and let's actually think like in this case, like the clock's actually perfectly synchronized. So so our T2, and let's say that actually like for simplicity, let's say for simplicity, A is 0. Okay. Our T2 is going to be 10 again. And our T1 is also going to be 10. So our clock offset is going to be 10 plus 5 minus 10, which is 5, which is wrong. We want 0. So we kind of like, we want to realize that here actually the offset of 0. But we incorrectly estimated as 5 because our like we assume that delay is symmetric while actually it is asymmetric. Okay, but well, that's fine. We'll record. So obviously, like estimated symmetric delay on the first iteration is going to just return 0. So the sample we'll end up with is what's in the sample offset delay? Offset is going to be 5, and delay is also going to be 5. Okay. What happens on the second iteration once we get to this loop? So the clock offset is going to be the same. Is going to be 5. So they actually, I mean, it wouldn't. Okay, yeah. So we okay. Should we just go and read the paper here? Should we just go and read the paper? I believe this is correct because it seems like it's uh, just table. Well, okay. Let's maybe try to write a test here. It's going to be hard because we also need time. Okay, let's just put a pin in this. Okay. This is like, this was right. Because yeah, what I'm confused about, it seems like, we like compute our current clock offset with the clock offset for the previous sample. But I mean, if like there is a persistent asymmetric delay and the delay is the same, like the offsets are going to be the same. So something doesn't add up here. Well, okay. Actually, if there is a bug, it doesn't really matter. It means that just our like clock synchronization is not precise enough because it doesn't like account for asymmetric delays. Okay, but okay, I'm extremely curious here right now. Okay, let me just take a look at this again because probably like it's like there's never a bug in the code which you haven't written. Like all the bugs are in your own code. If you look at someone else's code and you think it's a bug, it's probably you are not correct. So clock offset, and we compute the last clock offset, and what you pass as a clock offset is just like the data which we computed like from the same sample. Okay, yeah, this I'm going. I'm going on the record here saying that I don't understand this code and I think it is wrong. If I'm wrong, well, we'll all have a good laugh next week. If not, we also have a good laugh. So it's win-win situation anyway. Okay. Anyway, we've computed delay and we updated our source. Okay, and we set learned. Okay, so okay, apparently learn just accumulates samples. Then I guess another thing that like calls into the clock is the tick method, which just like ticks periodically. And okay, so periodically, if our current synchronized clock was synchronized long ago, we say that hey, actually, no, like our time is not good anymore, and let's just reset it. Otherwise, we do the synchronizing, which is interesting, which is probably actually the mid of the algorithm. Okay, so what is window elapsed? Okay, window elapsed is just like the time from the start of the epoch, and again we are looking at monotonic time here. Oh dear, we even have Joran in chat with us today. Okay, well, yeah. If it is a bug, it's Joran bugs, which is like a benefit of like reviewing code on Twitch, which was not written by you. Like, if there is a bug, probably you are stupid, but like if there is a bug, it's not your bug. Anyway. Finding bugs is good. Like just like if you don't find bugs in the code, then this is a problem because that means that you are not careful enough when reading the code because there are always bugs, no matter like how you test your code, how you prove your code. Like there's always something fishy there. Okay, going back to synchronize. So we check how much time elapsed. If if we were collecting samples for too future all of time, we do nothing. If we collected samples for too long of a time, I would expect to see window. Oh yeah, we just okay. We actually like we don't expire stale samples. We just reset everything. So this gives us a strong guarantee that epoch lives like between like window max and window. Okay. If we so now I get the meaning of this learn. This learn is probably for optimizing CPU time. So like now that we actually need to do some like computation to figure out what is the time, but if we haven't learned a new sample since before, it doesn't actually matter to do this computation. So if we haven't learned a sample, we return. Otherwise, well, we kind of like say, okay, learned false, we reset it. Okay, and kind of like a small tip, like you often do this like caching variables. You say, hey, if something happened, like it is true. If it didn't happen, it is false. And what I find useful is that it is like useful to include a reason. So for example, here we could say is not like learned bool, but it could be something like learned when, which is an optional of U64, which is like monotonic timestamp, or like given like this is like inside a tick, like tick count. So this isn't applicable in this case, but in general, if you include redundant information about why in your caching variables, that could make reading the code easier, and also like sometimes it could make finding the bugs easier, because like you could always learn you can always set bool to true at any moment in time. But for example, if you actually store timestamp here, then well, you cannot like randomly assign false here. You actually need to come up with a timestamp, and that's harder to do at random. But well, that's kind of like getting into the weeds. Okay, now that thing I've talked about, where we start. So we go and we find the smallest interval, which, given our current tolerance, still intersects the quorum of clocks. And if we found this, if we found this, okay, yeah, we say that, hey, this window is now our epoch, and we reserve a window and do, I guess this is just some login. Okay. So it's pretty clear. Okay, let's get into Marzullo's thing, which is actually which is another function which I've read the name of, and to this day avoided looking at the body of. Okay, so let's say tuples. What do we do here? Okay, yeah, we just use, as I've predicted, we use Marzullo tuples as a buffer for this algorithm. And for each sample in our window, we say that, hey, there is, okay, so basically we convert every sample, which is a point, into -1 minus tolerance plus tolerance thing. Although I'm kind of like, I don't understand why we add one-way delay here, because it feels like we should only be looking at the tolerance. Or, well, I guess okay, so this is actually also potentially incorrect. So, okay, I guess what this code is doing is that it adds a one-way delay to tolerance, which means, like, obviously, like, if it takes like 10 seconds to talk to a replica which is far away, it probably means that the clock on that replica are imprecise, which sort of makes sense. What doesn't make sense to me is that I think because we are adding the tolerance, this actually makes it easy to find this interval. So because with larger tolerance, you would find like it would be easier for you to find this interval which intersects a bunch of things. So what is Marzullo? Okay, what is the result of this function? This is interval. Lower bound, upper bound, sources true, sources false. So kind of like, I mean, I sort of want to say here that like upper bound minus Oh dear. Why? Okay. No. Oh dear. I've lost all my keys, lower bound. So I want to assert that this thing is actually less than equal our tolerance. And I think that's not true. I think that might not be true specifically because here we add our like one-way delay because it's I mean it's okay. This gets curiouser and curiouser. Uh, clocks, as I've said, like clocks are hard. You tend to lose your hair when you work with clocks, as you can see on my head right now. Okay. Well, before we go into this, let's check if we actually if we do. So okay, we set synchronized, and then real time synchronized. Okay, do we actually? Okay, well, no. Do we set epoch as synchronized? So we swap epoch here, but do we have? Okay, yeah, we set synchronized. So interval, lower bound, upper bound. Okay. So this one is actually I'm I'm not sure this is a bug because it seems that like we've actually if you exist in a cluster with very high delays, you might actually violate that constraint that the tolerance is like up to clock offset tolerance max because it actually might be worse. Okay, let's see how Marzullo's thing work, which is another paper which at least this one I've downloaded and I've looked like through it. So okay, the idea is clear. We like want to again, our sources are intervals, so we intersect them all, and there is at least every point on the number line will be intersected by some number of clocks. Some points are intersected by 0, some points are intersected by 1, etc. And there's going to be a point which is intersected by the largest number of intervals. And probably it's not going to be just a single point, probably it's going to be like an interval which is intersected by the largest number of clocks, and we want to find that interval. Okay. So we have a bunch of tuples, which is the source, offset, and lower upper bound. Okay, smallest interval. Sort tuples. Good question. What is less than for tuples? So we first compare by offset. And then lower bound before upper bound, and this is tiebreaker. Okay, so this makes sense. And I kind of I wish Zeke had some STD CMP compare by A B. Actually, I mean it could be STDX. So I wish we could say something like offset, and maybe if we are being cute, something like this, minus bound or something like that. So basically instead of manually writing this chain of if, you just pass the fields you want to compare and maybe flag some fields as negative, but well, it's too smart. Probably better to do it this way. Okay, anyway, so we sources our tuples according to the offset, and we sort lower bounds before upper bounds. And yeah, I guess what we're going to do is that we are going to just, like, do a linear scan, processing events, and just counting how many points intersect this event. So it's like, one-dimensional ray marching. This is probably how it is like properly called. Okay, so we go. Well, yeah, count is that number of things that intersect our interval. If we go inside the lower bound, then we increment it by 1. If we pass upper bound, we increment it by 1. If the count is less than best, then kind of like the current, and the next tuple is the end. Okay, yeah, actually, Marzullo seems pretty easy, at least as if you solved too many competitive programming problems when you were young. So I mean, just the linear scan, count how many things intersect, and then output large interval. Okay, yeah. So okay, this one I'm positively calling out as bug. So you see, in window tuples, we add one-way delay to our tolerance. And that, like, okay, suppose that, like, you implemented TigerBeetle and you use like avian carriers for your TCP IP. Like using pigeons for sending packets. So your like delay is like minutes or hours. And then you get here, and your tolerance is actually pretty small. It's like 20 milliseconds. But then your like one-way delay is like an hour. And you got a like Marzullo tuple, which is like -1 hour plus 1 hour. So of course they all are going to intersect. And of course we all like are going to have like some interval. And that means that we'll actually get a non-zero interval, and we'll say that our clocks are synchronized. While in fact, I think actually it should, like, it probably should be the opposite. Like, if if the pings are very take a lot of time, we probably should have less certainty about our time. And at some point, like, I mean, like, it's like it takes like 2 years to exchange time. Then you just shouldn't, you should be unavailable because you wouldn't be sure about your clock. Okay, so yeah, okay. This okay, so this actually was fruitful, because I've looked at the two functions which I previously haven't looked like asymmetric delay and Marzullo. Well, yeah, no, Marzullo itself is like legitimately looks like correct. I don't see any problems in the code, but like this window tuples logic definitely looks suspicious. So again, maybe I'm wrong, maybe I'm right. Let me like quietly read the papers, read the code again, maybe write even some tests, and next time we'll learn who is right or who is wrong, or maybe like Joran's watching this stream, so maybe next week I'm not working in TigerBeetle. But no, this is definitely never going to happen, because like, I mean, finding bugs is the purpose of this whole thing. And like in general, like, there's like two reasons why we do this like TigerBeetle thing. First of all, because like TigerBeetle does use a bunch of very exciting technology, old and new. Like this thing in particular, Marzullo's algorithm is like very old, but still it's like cool tech to know about. And it is like, if you know something, it is just your duty to teach other people about this thing, because like it's useful to know things. It adds to the world value. So that's kind of the first reason, like just to tell the story. And the second reason is, well, like, you read this code on the stream, you read the code in a different context, and that makes you more sensitive to other kinds of bugs. Because I've looked at the code for clocks like many times, but I haven't noticed these two particular smells, which again, maybe they aren't actually bugs, but maybe there is. We'll learn next week at 5 p.m. UTC live on Twitch. And if you manage to miss a Twitch, the recording is going to be on YouTube as well. Thanks you for watching, and let's hear our awesome outro track.